This is my 50 MHz Pierce crystal oscillator circuit. As we know about the crystal oscillator circuit, it consists with the amplifier block and the feedback network block. So let's talk about the amplifier block first. So for the amplifier block, I'm using an unbuffered CMOS inverter with a feedback resistor that connected with the inverter. So this inverter provided 180-degree phase shift that we needed. And this RF feedback resistor is biasing the inverter to its linear region in order to provide gain for this system. So the RF that I choose is 1 mega ohms for biasing the inverter. So now let's move on to the feedback network block. So in the feedback network will provide the frequency for the system, which came from the crystal. So since I'm designing a Pierce crystal oscillator, the crystal that I choose is a parallel mode crystal, and for a parallel mode crystal, it's only oscillated when you connect it with this certain load capacitance. When you connected the crystal with certain low capacitance, the crystal can oscillate at its desired frequency. So for my crystal, the low capacitance that's specified on the data sheet is 10 picofarad. So I connected with 2 capacitors. And as crystal concerned, these 2 capacitors is actually in series as a crystal concern. So the value that I choose for this 2 capacitors is 22 picofarad. So in series, the value is approximately at 10 picofarad. But for the feedback network, it not only provides the frequency that we needed, but also it need to provide another 180-degree phase shift. So this resistor and these capacitor provide a 90-degree phase shift, and the crystal and this capacitor provide another 90-degree phase shift. So added up, the feedback network provide a 180-degree phase shift to fulfill in the Barkhausen criteria for this circuit to oscillate. So for this resistor is not only provide the phase shift that we needed, but also it's controlling the drive level of the crystal. And now we look at the wires, and this wire is the output of the whole system, and this wire is the ground for the whole system. And this wire is for powering up the inverter. In the data sheet for the inverter, the supplying power is recommended from 2 volts to 5 volts, and for this design, I choose 3.3 volts for powering the inverter. And as the data sheet specified, if we power the inverter at 3.3 volts, the output voltage of the inverter should be around 1.65 volts to 2 volts. So now let's plug the output to the oscilloscope to look at the result. So now we look at the power supply. The power supply is around 3.2 volts, approximately around 3.2 volts. And now look at the circuit. So we provide this power supply, and this is the connected to oscilloscope. So now we look at the oscilloscope. As we can see, the frequencies at 50 megahertz, and the peak-to-peak voltage is, as we expected, should be at the range from 1.65 volt to 2 volts. And the falling time and rising time is pretty decent. For the falling time is around 5.6 nanosecond. For the falling time is at around 6 nanosecond, and the rising time is around 6.3 nanosecond. So basically, this is the waveform that I got from this 50 megahertz Pierce crystal oscillator. And this is my demonstration. Thank you for watching.